Hello, my name is Martina Heller and I'm going to present you a custom cryogenic transfer unit for a commercial LEAP. Why do we need a transfer system? So when you want to do a lift-out sample from an aluminium alloy and you want to fib it with a gallium fib, you will have the problem of liquid metal embrittlement at room temperature. So all of the gallium from your fib beam is diffusing into the grain boundaries of the aluminium, and the grain boundary is not representative anymore of the original composition of the aluminium alloy. Another example are new energy materials, for example the SCALM system. This SCALM system is based on the theory that you have a gallium droplet on a support material. In this gallium droplet there are atomically dispersed catalyst material, for example palladium or platinum atoms. When you want to investigate these systems further, you want to do maybe a lift out, but the gallium melts at room temperature. But at cryo temperatures, you can't deposit some platinum on your sample. So you face there some problems. So you need a transfer system with a controlled atmosphere. You can do cryogenic or room temperature transfers with this system, and maybe you want to have also the possibility to do a lift out at cryo temperatures. Our transfer system connects the FIB-SEM with the atom probe. So you see here our FIB-SEM transfer arm with whom we are able to insert and retract samples on our cryostage inside the FIB-SEM. To this FIB-SEM transfer arm we can attach our atom probe transfer arm, what you can see here. The sample exchangement you can see in this small video. You retract your sample shuttle, where you can see here our atom probe tip, and here our bulk material, maybe for the lift out. Then you can come with the transfer rod from the atom probe transfer arm, and then you can get your sample by just screwing out of this transfer shuttle, and then you can retract your atom probe transfer rod into the atom probe transfer arm. This atom probe transfer arm is actively cooled by liquid nitrogen and maintains the vacuum. In addition, we have here a cryo load lock on our buffer, attached to our buffer chamber of our LEAP. Inside this the buffer chamber is, with this additional part, a cryo stage. So this is our LEAP, where I can see here the additional part, and inside is our cryo stage, which you can insert into the buffer chamber. With the attached transfer arm, you can pump down here the cryo load lock. Then you can, at a certain vacuum, open the valve here when they have the same vacuum, wait until the vacuum gets better. During this entire time, the sample is here inside, actively cooled by liquid nitrogen from this dewar. When a certain pressure is reached, you can insert your sample onto a special designed cryopack on the cryostage, just by retracting the rod inside the atom probe transfer arm and then screw your sample with the atom probe tip into the cryopack. After you screwed it in, you can retract the atom probe transfer rod into the atom probe transfer arm. You can close the valve and start with the investigations. So this stage inside the buffer chamber is also possible to heat your sample. So it's an in situ heating and cooling stage. It stabilizes the LEAP cryo shuttle, and also it enhances sample transfer. During the entire time, your sample is actively cooled by liquid nitrogen. Our atom probe transfer arm can be also attached to our PVD deposition and electropolishing station, also to the new build AUX-CAD, the titanium atom probe. So our transfer system maintains all the time a high vacuum from 10⁻⁵ to 10⁻⁶ millibar. It maintains -160 degrees Celsius during the transfers. You see no frost formation on your atom probe tip. And in addition, you have short transfer times into the analysis chamber. The last transfer I made took me just 30 minutes from the FIB-SEM into the analysis chamber when I started with my measurement. At the end, I just want to show you our first results. So we prepared an aluminium tip inside the FIB-SEM at -140 degrees Celsius. We transferred it into the LEAP at -160 degrees Celsius. We saw no frost formation, and in our measurement we saw a grain boundary with no gallium at all inside the grain boundary. For the new energy materials, for the SCIM system, there are still challenges to face. So up to now we heat the system up to 0 degree to enable the platinum deposition, and we are about to develop a new cryogas system that enables also deposition at cryogenic temperatures. So in general, this transfer system enables us to work on these two systems and opens also up to other material classes and research fields. At the end, I want to thank our team, and if you have some questions, you can write me a mail. Thank you.